We all think of the internet as this magical cloud, right? But what if I told you it's actually a physical system? Seriously, it's governed by these invisible rules, a sort of network physics that controls how every single bit of data moves around. And the absolute core of that system, kind of like its fundamental law of motion, is a protocol called TCP.
I mean, think about it. Every single second, trillions of data packets are just flying across the globe. It's this beautiful, chaotic, high-speed ballet. So what's the invisible force that keeps it all from descending into a catastrophic worldwide traffic jam? What keeps the entire system from just grinding to a halt?
Well, the answer is a protocol called TCP, which stands for Transmission Control Protocol. The best way to think about it is as the internet's master rulebook. And it's so brilliant because it solves two huge problems. First, it makes sure your data actually arrives in the correct order with no missing pieces. And second, it stops the network from being completely swamped by all that traffic.
So let's tackle that first problem, reliability. How in the world can two computers, total strangers on the massive internet, start a conversation that they can both trust? Well, they need a formal introduction. And that process is what we call the TCP handshake.
Okay, so it's basically this very polite three-step dance. First, your computer, the client, sends out what's called a SYN packet. It's basically saying, hey, I'd like to talk, and I'm going to start numbering my pages at number X. Then, the server, on the other end, replies with a SYN-ACK. That means, loud and clear, I'll start my page numbering at Y, and hey, I see you're starting number X. And to wrap it all up, your client sends one last ACK to say, Roger that, I've got your page number Y. Boom. Just like that, you've got a connection. Now, you might be thinking, this seems a little formal, right? Why not just a simple hello and hello back? Why do we need that third step? This is where the real genius of TCP's design for reliability really starts to shine. And here's why that third step is absolutely crucial. Both sides need to synchronize their starting points. They do this by agreeing on what are called initial sequence numbers, or ISNs. Think of it like you're about to read a book with a friend over the phone. You both have to agree on which page number to start on, right? The three-way handshake makes sure both the client and the server have acknowledged each other's starting number. This synchronization is what lets them track every single piece of data, making sure nothing gets lost, nothing gets duplicated, and nothing gets out of order.
And that right there is the first pillar of TCP. That three-way handshake isn't just a friendly greeting. It's the core mechanism that builds a trustworthy, ordered, and totally reliable channel for communication over this inherently chaotic thing we call the internet.
Okay, so we've got a reliable connection. Awesome. But now we have to deal with the second, and honestly, even more dramatic problem. How fast can we actually send data? I mean, if everyone on Earth sent data as fast as they possibly could, all at the same time, the internet would just break. This is the problem of congestion.
The danger here is a really scary scenario called congestion collapse. This is when routers, the traffic cops of the internet, get so completely overwhelmed that they just start dropping packets, just gone. The whole network enters total gridlock. And the craziest part is sending more data actually makes everything worse. The total amount of information getting through actually goes down. It's like a digital black hole, and TCP is designed specifically to keep us from ever falling in.
The guiding principle behind how it does this is actually pretty simple. As the legendary book TCP/IP Illustrated puts it, the approach is proactive. TCP doesn't just wait around for a total collapse. It's designed to slow down the moment it even thinks there might be trouble, easing off the gas long before an accident happens. But how does it know? How does it know when to slow down? Well, the answer is in this brilliantly named and incredibly clever algorithm called slow start.
So, how does slow start work? Well, think of it like you're a driver on a highway you've never been on before. You're not just going to floor it, right? No way. First, you probe. You send just a tiny bit of data to test the waters. Then, for every little piece that comes back acknowledged, you send two more. You're basically doubling your speed every single time, accelerating exponentially to figure out just how fast this road can go. But the second a single packet gets lost, that's your signal that there's a traffic jam up ahead. You slam on the brakes and immediately adjust your speed. It's brilliant.
And you can see that exponential growth right here. This thing called the congestion window, which is just how many packets TCP sends before waiting for an OK, it doubles with each successful round trip. So you go from 1 packet to 2, then 4, and so on, ramping up incredibly fast to find the real bandwidth that's available at that exact moment.
Now, TCP doesn't just stay in this super aggressive mode forever.
Once slow start finds the network's limit, by causing that packet to drop, it shifts gears into a much more sustainable phase called congestion avoidance. The goal totally changes. It's not about finding the speed limit anymore, it's about cruising just under it. So the growth becomes linear. It's a much more gentle, additive increase, carefully using the network's capacity without ever pushing it over the edge again.
And at the end of the day, this dynamic, two-speed approach is what gives the entire internet its stability. It lets every single connection be aggressive when the road is wide open, but also be cautious and respectful when traffic starts to build up. It's this fundamentally cooperative system that prevents any one of us from ruining the internet for everybody else.
So let's just bring these two huge ideas together for a second. On one hand, you have the handshake, which creates a totally reliable conversation. And on the other, you have congestion control, which manages the speed of that conversation.
These two mechanisms, they are the true unsung heroes of the internet. The handshake gives us that rock-solid foundation of reliability, making sure every message is heard correctly. Then, congestion control acts like this dynamic throttle, making sure the whole system stays stable and efficient, even with billions of us using it. It's reliability and stability, working together in perfect harmony.
So the next time you're browsing a website or streaming a movie, just remember, it's not magic, it's physics. The internet works because of the unbelievably elegant, intelligent design of TCP. And it kind of leaves us with this big question for the future, right? As we design the next generation of networks, what lessons can we learn from this beautiful, delicate balance of pure caution and raw ambition?